Okay, with respect to the quiz, I will, so I got back this weekend. I'm going to post up the actual quiz problems and a key for the quiz as well, so you can try to figure out what you did wrong. If I can figure out how to display the answers you put down, if I can figure that out, I'll have that posted as well. All right. Any questions about the quiz at all? Oh, it's posted on D2L right now. Yeah, everybody's, sorry. Yeah, everybody's grade is posted on D2L. The average score for this section was about an 81, so you did pretty well overall. I know some of you didn't do as well as you probably expected to do. There are some errors on things that maybe should have been easier, like the vector problems, I guess some people missed, probably shouldn't have missed. There were a lot of people missed the one on the some people missed the problem on which combination of the X and the T and the V and A made sense. That was just basically figuring out which one has a consistent unit, because if you add things together with meters per second plus meters, that doesn't make any sense. They all have to have the same unit. Okay. All right. Maybe the one a lot of people missed also was you have two balls. One was dropped equals 0, one was dropped 1 second later, right? And then what happens to the difference in the speeds between the two? Just think about what's going on with the velocities of the balls. So one, basically the velocity is just going up linearly with time, it's proportional to t. The other one is also proportional to t, but it starts at a later time. But the fact is both curves are linear in t. They both have the same slope, so the difference remains the same. Does that make sense? If you were to plot the velocity versus time for both of them, they would just be parallel lines. And so the difference between the two would remain the same. Okay. Well, let's go on. Though let's review some stuff that we covered last week, but because time marches on, there's we have all these quizzes, right? All these quizzes. So there's a quiz coming out next week, this Monday. So we're already getting ready for that. And you already know most of the material, but let's do a problem together. Okay, we'll do clickers more towards the end, but let's do one problem together. So if you're not familiar with how to do these relative velocity problems, they can be a bit tricky. So let's see if we know how to do this. Oh yeah, let me thank you. Okay, we're back. Okay, so let's say a boat is traveling at, let's say, 30 kilometers per hour. Due means exactly or perfectly west relative to the ground. Okay. If the water is moving 10 kilometers per hour due north relative to the ground, what is the boat's velocity relative to the water? Okay? So, just stop and think, do I know how to do this problem? How would I do this? So let's do it together. Okay, first, let's draw some coordinate axes. Let's take the usual thing. So north will be my positive y. East will be my positive x. And then west will be negative x. south would be negative y. Okay, now they say ground. Ground is this thing that I can view as not moving. Okay, so having got this for a while, it's very often simplifies the problem if you just don't say ground. You just say the velocity of the boat. Okay. The point is the ground is the thing that's not moving, so you don't always have to say relative to ground. Relative to ground. You just say the velocity of the boat is the following. Okay, so what do we know? So the boat, we say, is 30 kilometers per hour west relative to the ground. So I would say the boat, just the velocity of the boat, the relative to the ground is implied, is which? Okay, so if I write this in terms of I hats and j hats, what would I write here? Would it be positive or negative? Yeah, negative. And then which? Yeah. So is it I hat or j hat? Yeah, perfect. Okay, so minus 30 kilometers per hour I hat. Okay, it's going like this. And v water, we are told it's moving 10 kilometers per hour relative to ground north. So I'll just say v water is 10 kilometers per hour. It's going in the north direction, so j hat. Is everybody good on that? Let me see if I'm sure the focus is good. All right, now we want to know the boat relative to water. So what I can write down, I can write it in several ways. So I'll write it two different ways. So one way to write it is boat relative to water. And I write it out completely so that it's clear what I'm saying. So this says boat. It's hard to read because my handwriting's not so good. So the boat relative to water would be the velocity of the boat minus the velocity of the water. Okay. This is the velocity of the boat as seen by the water. So you take the velocity of the boat, you subtract the velocity of the water because I'm the water, I'm watching the boat, I'm going to subtract my velocity to get it. Okay? If you like this, write it this way. If you prefer to think of it in another way, you can also think of this way, that v boat is equal to the velocity of v water, the velocity of the water, okay, plus the additional velocity of the boat relative to the water. Relative to water. I know some students like to think of it this way. The velocity of the boat is the velocity of water plus the extra amount the boat moves relative to the water. That is conceptually kind of easy to understand. Okay? Any questions? All right, you can use either one. Let's use the second one. So we have the velocity of the boat. It's negative 30 kilometers per hour I hat is equal to the velocity of water is 10 kilometers per hour j hat. And now we have the velocity of the boat relative to water. Okay? And so now we can solve for the velocity of the boat relative to water. It will be minus 30 kilometers per hour I hat. And then bring the 10 on the other side, so it becomes minus 10 kilometers per hour j hat. Okay, any questions? So if we were now going to get magnitude and, okay, so I guess the problem said, what is the boat's velocity relative to water? Okay, so actually realized in my notes I'd written what is the direction, not the magnitude as well, so I might as well, you're going to need to calculate that. So it will be squared plus 10 squared. Okay, so if I want to know what is v, the speed, so without the vector hat, relative to water, that will be the square root of 30 squared plus 10 squared. Does everybody follow me on that? Because we have these two components. Okay. So if I take the x component squared, y component squared, okay, if you prefer to put the minus signs in, we can put the minus signs in and square them if they don't do anything. Okay, that comes out to 31.6 kilometers per hour. Now if I want to get the direction, I can draw, here's the plus x x-axis plus y-axis. Okay, we're moving negative 30 over here, so negative 30 like that. And then we're moving negative 10 like that. So this guy is the direction. Right? If I want to get this angle, all right, if I want to get this angle, this theta, tangent of theta, what will tangent of theta will be? Well, tangent of theta is this side divided by this side. You don't put the minus signs in when you say the side of the length of the triangle, so it will just be 10 over 30. Okay, so I'll have 10 divided by 30. And so I end up with theta is equal to, it will be 18.4 degrees. Okay, it's a small angle, so the calculator will give you the right value. It's 18.4. You don't have to subtract 180 or add 180. And the way I would describe this, so this direction is west, and so this theta would be, so I'd say 18.4 south of west. Okay? Yeah, question? Yeah, so this is, so it's the boat relative to the water, which is the river. Okay, yeah, we are given, so we start off with knowing that the boat is moving, this is going directly west relative to the ground. And we know that the river, or the water, is moving 10 kilometers per hour north. So the boat relative to the water has to be a little bit like that, in that direction, a little bit south of it. Because the water will make it drift up so that it ends up going due west. Any questions about this? Okay, good. That was just to get things started, make sure we connect with things from last week. We'll do more of these reviews. Okay, so now we're going to talk about something completely new. We are already in chapter 5, and we're talking about force. Okay, force, I'm going to give you a very wishy-washy definition because it's a little bit complicated to give you a better definition of this. And every textbook at this level is saying the exact same words. And a force is a push or a pull. Okay? So I can push you, or you can push me, or I can pull you towards me, or you can pull me towards you. Pretty much. Okay. Right. By the way, the reason why these definitions of physics are kind of, in my opinion, a little bit vague is because in order for the human mind to understand something, what you typically do is you decompose something complicated into something simpler. However, right now we're trying to describe the most simplest things that we understand. And there is no other concept simpler than the idea of a force. So we'll talk about mass. And how do you describe mass in terms of things that are even simpler? We can't really do that. Right? So that's why it's a little disappointing. I give you this slightly wishy-washy definition. But it's simply because our concepts of everything are a little bit, everything we know is a bit more complicated than force that we're talking about. Okay? Do you understand what I'm trying to get at? If I were trying to describe how a mechanical pen, how a mechanical pen works, I could talk to you about the spring, about the ink, and all that stuff. But if I'm talking about what is the mass of this object, then I don't have words that are simpler than the word mass to describe it to you. You get what I'm saying? It's a similar thing to here with force. It's a little complicated to describe. Okay, but the actual concept in physics is actually very well defined. So the force, which we will write as F, capital F. Usually there's some subscript here or something to denote what force we're talking about. So the force F is a vector with units of newtons, capital N. So named after Sir Isaac Newton, who his name is going to appear all over this lecture because he did so much of this stuff in the 1600s in England. So 1 Newton is, so that's a Newton, is equal to 1 kilogram times, and it's a little bit complicated, meters divided by seconds squared. So this is our kilograms. This is meter. There's a square on the seconds in the denominator. Okay, that's the definition of the Newton. And the reason why it's a little complicated will be clear in the lecture in about 5 minutes from now. The next thing we'll talk about is what's called the net force. Net as in total, okay? For example, what is your net worth or your net force, the sum? Okay, so the net force on an object is the vector sum of all forces on the object. Okay, so very simple. So F net, and we'll talk about F net all throughout this course. You just sum up. So are people okay with the symbol? This symbol means sum. You sum over everything. So sum over all forces on an object. And let's just write it as F. You might put a subscript here to tell you there's some index here, but let me just write it this way. Okay, so the net force is the sum of all forces on an object. Remember, the way you add forces together is you think about each component gets added together. Okay. So you do the x components together, you add the y components together. All right, the first thing we'll talk about with these forces is Newton's first law. Okay, and there's various ways of defining Newton's first law. I will give it to you in, I think, the most simple operational form. So the way it's maybe easiest to use. So my statement is if the net force on an object is 0, then the acceleration is 0, and the velocity is constant. You can deduce that from the fact that the acceleration is 0. Okay? So if I say something has 0 acceleration, because acceleration is the time derivative of the velocity, acceleration equals 0 means the velocity doesn't change. Okay, so I can make this as a little diagram. So this is Newton's first law. I can write Newton's first law like this. The net force is equal to 0. Now, how many of you know what this symbol means? You've seen it before somewhere, right? Yeah, all it means is one implies the other implies the other. Both ways, it goes both ways. It's a double arrow, okay? They're equivalents. So what I'm saying is, if you know that the net force is 0, you know that the thing over here I'm going to write is true, but it also goes the other direction. So you can say that the acceleration of the object is 0. If the net force is 0, the acceleration of the object is 0. And then there's another thing here, but all three things are equivalent to each other. They imply the others too. The other thing is that the velocity is constant. Okay, if you know the velocity is constant, the acceleration is 0. If you know the acceleration is 0, the net force is 0. All of them are equivalent. So what does this mean? This means that if I look at this ball here, the acceleration appears to be pretty much 0, right? doesn't seem to be moving very much, okay, as you see it. And so the net force is 0. Now, the little tricky thing is if the ball is, suppose we're in outer space, because gravity is mixed into a opposite. But suppose we're in outer space, and you saw this ball just drifting. You've probably seen videos from like a space station or something, right? Something just drifting in space like this, like a drop of water. What is acceleration of something that's just drifting in a straight line with a constant speed? Yeah, 0. And so this thing would also have net force 0. Okay. So the fact that the velocity remains constant means that the acceleration is 0, which also means that the net force is 0. So whenever you have forces on an object that are all balanced out to cancel out, that's when you have the net force 0, and therefore the acceleration is 0, and the velocity is constant. Okay. Now there's a specific case, so if the acceleration is 0 and the initial velocity is 0, then it will just remain at rest. It will just stay there as well. But that's a special case with constant velocity. Any questions about this? Okay, very good. The next thing I want to say is there's this word that's called equilibrium. All right, so when the net force on an object is 0, we say the object is in equilibrium. Okay, so that's another terminology, but it just means F net is equal to 0. So here's another thing I can say. Equilibrium is also the same thing as saying the net force is 0. The object is in equilibrium. Very simple example. Suppose we have a little block of mass, and let's suppose that there's a force acting like this. Okay, but there's another force acting on this object, and it's in the negative direction with the same magnitude. Then the net force on this block will be F plus negative F, and that will cancel out to 0. And so we would say that this thing is in equilibrium. And if the net force is not 0, then we'd say it's not in equilibrium. Any questions about this so far? Okay, now I'm going to hit you with a couple more definitions. One is something called inertia. So, inertia. All right, the concept of inertia is the idea that suppose there was a little piece of chalk, and I were to throw it at you, just toss it at you 10 meters per second or something. You'd say, oh, that's kind of annoying, but you wouldn't be terrified by this piece of chalk. Right? But suppose there was a truck coming at you at 10 meters per second, you would jump out of the way because it would kill you. Okay? So there's a difference between an object moving with a certain velocity that's clearly very small versus something that's really massive. So this concept of inertia is related to that fact that inertia is the tendency of an object to maintain its velocity. Okay, and the first law tells us, I'm talking about the first law of Newton, Newton's first law, tells us that the velocity will not change unless there is a non-zero net force. Okay, so inertia is the concept that all objects will basically have constant velocity unless they're pushed or pulled by some net force. Just think about things in outer space. They just float in straight lines with constant speed. They just float along like this until you bang on one of them, then they change their direction, and you put a net force on the object. Good. Now, the next thing I want to talk about, we're not going to do anything really with it, but I just wanted to mention the terminology because everything we're about to do is related to something called an inertial frame. So inertial frame, this is basically a reference frame. Okay, you might ask the question, what the heck is a reference frame? It's just basically the way you are viewing a system. So any observer, you, me, anybody on a train, maybe on a boat, on a car, they look at the world and they record what they see. This is what I mean by a reference frame, some observer. A reference frame that is not accelerating. Okay? So for most purposes, the surface of Earth is a good reference frame, is a pretty good inertial, oops, I can spell inertial frame, right? A really good inertial frame is something that is not moving relative to the stars in the sky. Those stars in the sky are pretty good inertial frame. The reason why the Earth is not really an inertial frame is because we're spinning. In fact, the Earth is, every day the Earth spins, and that causes a centrifugal acceleration pointing towards the center of the Earth. On top of that, the Earth is actually going around the Sun, and so there's centrifugal acceleration caused by that. But it's not a whole heck of a lot. So for most points of view, for problems that we're doing, we can think of the surface of the Earth as an inertial frame. The reason we're making this comment about inertial frames is if you are in an accelerating frame, if you're like, suppose this room was spinning 100 times per second, all right? We'd all be like stuck to the wall like this, okay? So the laws of physics would be everybody hits the wall and gets stuck, right? That's because it's a different system. It's not an inertial frame. There are laws of physics that are kind of weird in this accelerating frame. So we're not doing that. We're doing a simpler case. Okay. Next thing I want to define is more something you already know. So it's mass. Mass. And it's very important. Okay? And I'm going to give you a total cop-out definition. I'm going to connect it to another thing I didn't really define well. And it's basically how much inertia an object has. Okay? Now, as I said, it's kind of difficult to define mass because it's kind of more basic than everything else we talk about. But let's just go on with this, and I will try to fill in some gaps here so that it's not quite so mysterious. So first of all, the unit is the kilogram. We already talked about this, kg. It started off being the gram, but they realized later that the gram was kind of small for most things, and so they bumped it up to kilograms. So it's the only unit where there's a prefix for the standard unit, kilo, in front. Now, one thing I want to say is that mass is not weight. Okay? So weight has to do with gravity, the force of gravity, and we're going to talk about that next time, not this time. Okay? Mass is inherent to an object. Mass is a property, inherent, meaning it belongs to the object and it's not dependent on where you are property inherent to an object, meaning that a 4 kilogram mass is 4 kilograms on Earth. It is 4 kilograms on the moon. It's 4 kilograms in outer space. It never changes. Whereas when we talk about weight, it will depend where we are, how strong gravity is. We'll talk about that later. Okay. You might ask the question, how can we separate mass from weight? Right? That's a good question because if I were to ask you, how do you measure your mass? You'd say you go, well, okay, how would you measure your mass? Scale. It's pretty much the only thing you know. So that actually measures weight. Okay? Even though if you have a metric scale, one that doesn't say pounds is actually measured for us. But if you have a metric scale, it will say kilograms, but it's not actually measuring your mass. What it is measuring your weight, and it's dividing by g. It's 9.88 per second squared. Right? So it's converting it for you. It's doing some math for you. But there is a way to actually measure your mass, and this is something you can use if you're in outer space. So just think a conceptual question. Suppose you're an astronaut in the space lab. It's the space station. You want to measure the mass of this eraser, and there's no gravity, so you can't put it on a scale and weigh how heavy it is. Does anybody know how you can measure that? Yeah. This is it's a little tricky because of putting it in water and the displacement. It's hard to contain the water as well. But that's a good idea. You can measure volume that way for sure. Yeah.
Apply a force and see how much it accelerates.
Yeah. That's kind of the trick. If you apply force and see how much it accelerates, you can actually measure the mass. So one way you can do it is you can actually attach it to a vibrating spring and see how fast it wiggles. So the more massive it is, the slower it wiggles for a given spring because it's harder to change the velocity of the mass. But if it's really small mass, then with a strong spring, it will vibrate very quickly. So that's actually one way you can measure mass without gravity at all. So we'll come back to this more later. Now, so I'm saying that it's not weight. Weight has something to do with gravity. Mass is just how much inertia it has, okay, how much stuff. You just want to think very simply, it's how much stuff is in it. Okay. All right. Now we're going to talk about Newton's second law. This is the biggie. If there's one equation that you're going to use everywhere in this course, it's this one. Okay. So if there's one thing if there's only one thing you learned from this class, from all of these crazy lectures from this professor in Michigan State, your freshman or sophomore year, it's going to be the Newton's second law. All right. If there's one thing, it will be Newton's second law. So Newton's second law. Okay, so we're assuming we're in an inertial frame, so we don't have any crazy laws of physics here. We will say that F net, so remember this is the net force, the sum of all the forces on an object, is equal to the mass times the acceleration. So this is the mass, and this is the acceleration. F net is equal to m times a. Okay, so if I want to solve for acceleration, maybe one of the ways we'll do it is just by saying, if I know the net force, if I divide by the mass, then I can solve for the acceleration. Okay, that's pretty straightforward, just divide by m. Now, how do we use Newton's second law? Well, we can do it component by component. So in terms of components, we have that the x component of the net force, so let me write this as F net comma x, is equal to the mass times the x component of the acceleration. Okay? And for the y component, F net y is equal to the mass times acceleration in the y direction. questions about this? Okay, note that the units work out right. So this guy, we said it has units of newtons. Units of newtons, which I said was 1 kilogram meters per second squared. Okay, and so now we can see why this is the correct unit. If I look on this side, this is mass, which has units of kilograms. Okay, and the acceleration, which has units of meters per second squared. So this is cooked up to have the right units. Okay, any questions about this? All right, now while we're talking about various quantities and mass, it's good to also talk about something. In the old British system, which is not so old and irrelevant because it's what you probably are most familiar with if you grew up in the United States. Okay, so this is what we use in the U.S. A pound is a unit. It's not a unit of mass, though. Okay, so it's a unit of force. So when you talk about how many pounds you weigh, that's talking about the force. And this is a unit of force, and 1 pound, 1 lb. Okay, so it's a funny symbol for pound, lb. It goes from the Latin word, where it comes from. It's related to, there's a complicated story behind that. But it's about 4.45 newtons. Okay? So if you wanted to convert it the other way, 1 newton is about 0.225 pounds. Okay, any questions about this so far? All right, in the time remaining, we're going to do some clicker questions. And I'm going to try to start doing something a little different. I have, okay, so I've told you I taught classes like this when I was at North Carolina State University many years, and I have tons and tons of practice problems from doing that. So I'm going to try out doing some clicker questions from a practice test that we use. It was actually a real test. It wasn't a practice. It was a real test. Okay, so let's look at this. So you'll see some funny things, like you'll see here, this is the mascot for the UNC Chapel Hill Rams, because that was our rival. So you'll see the cultural references there. Okay, let's do number 6. Here, let's focus it. Okay, the problem is a baseball is thrown by an outfielder with an initial velocity of 33 meters per second at an angle of 30 degrees with respect to the horizontal. How far does the ball travel horizontally if it is caught by the third baseman in the air at the same height from which the outfielder threw it? Okay, so A is 222 meters, B is 111 meters, C is 192 meters, D is 96 meters, and E is 56 meters. And I'll open up the polling. Oops, just 1 second. Now it's open. So remember the steps that we said to do. First step is get the components of the initial velocity, x component and y component. The next step was figure out which direction determines the x or the y direction determines the time, okay, the final time from the time. So the y or the x. And then you solve those equations to get the time, and then you use the other set of equations if necessary to get the distance or whatever you need. We're running out of time. Let me give you a hint so that you're struggling. The time turns out to be 3.37 seconds. If you need that to finish the problem, 3.37 seconds. Okay, I'll give you another 30 seconds to wrap it up, and then we'll just go quickly through the solution, and that'll be it. Okay, if you haven't already made a choice, go ahead and make your best choice. Let's see what people have said. All right, a lot of people said D. Let's go very quickly. I know we're running out of time here. Okay, so first of all, we get the components of the initial velocity, 33 meters per second at 30 degrees. So we can get the components. X component is 33 times cosine of 30, 28.6. Y component is 33 times sine of 30 is 16.5. I'll post these solutions up on D2L, don't worry. Okay, so in order to figure out the time, we need to know it goes up and it goes down. So that will be the y motion that determines the time, because it starts from the same height as where it ends. So we have y minus y0 equals 0, and that's 1/2 ay delta t squared plus v0 y delta t. Plug in all the numbers here, and notice that we have a 0 on this side. So we don't need the quadratic equation. We could use the quadratic equation, but we're lazy. So we divide by delta t to both sides, and we can get 4.9 delta t equals 16.5, and delta t equals 3.37 seconds. Then we can go to the x direction, x minus x0. Since there's no acceleration, it's just v0x times delta t. 28.6 was the initial velocity times 3.37 is 96 meters. Okay, I'll see you guys on Tuesday.